Welcome, everybody. Thank you for joining us in the Galaxies parallel session. As a reminder, I wanted to ask you to, follow our code of conduct. If you are not, if you don't remember it, there are in the web page, you can find it. And without further ado, I will introduce our first speaker, which is going to present some brief summary of the activities of the Galaxy Science Collaboration. Sugata, Kaviraj.
Okay, thanks, Mireia. Okay, so how do I move forward? Oh, yeah. Okay, so thank you all for coming. I'd like to give you guys just a very short summary of what we do in the Galaxy Science Collaboration. So my hope is that some of you, if you're not a member of the Science Collaboration, you would consider joining after today's session. So Simona May and I currently co-chair the Science Collaboration. We have 250-ish members. New members are always very welcome, so there are no requirements on the amount of time that you have to put in to join the Science Collaboration, so please join. So as you can imagine, our core goal is to perform extragalactic science over cosmic time with LSST data. And just as a summary of some of the things that we expect from LSST, of course we have revolutionary statistics across the full kind of spectrum of things that we want to do in terms of extragalactic studies. You'll hear more about this later, but there's a vast discovery space in what we call low surface brightness regime, right? So this is essentially the faint regime which other surveys can't access by definition, right? So LSST will allow us for the first time to access sort of low surface brightness flux and the kinds of things that you can do, at least in terms of extragalactic work, are things like you can access dwarfs outside the local group, right? You can look at things like intragroup and intracluster light. You can do science with sort of faint galaxy outskirts, tidal features driven by mergers and so on and so forth. Then there are statistical studies of very rare objects, so high redshift galaxies or extreme objects like starbursts and things like that. And of course, then there is an intersection with computer science. So lots of our SC members are developing new technologies via things like, let's say, machine learning, which will be important for understanding or using LSST data to understand extragalactic populations, simply because the data volume is so large. Okay, so if you want to get a feel for, if you want to get a broad overview of the kinds of things that we are thinking about doing, you can have a look at our roadmap. So there's a version of our roadmap on arXiv, so it's the one on the left here, and a breached version of our roadmap was also published in Nature. In Nature Reviews in Physics. I think this was the first ever volume of this journal, and as I said, a short version of our roadmap is available here. And these roadmaps will be able to give you an idea about the full spectrum of science that we expect to do in our collaboration. Okay, so I'll just give you a brief overview of how we are organized. So we have 7 working groups. So you can see the working groups on the left. They usually have most working groups have 2 chairs. Some of them sort of don't have 2 chairs at the moment, but we have regular elections where we kind of refresh our working group leadership. So our working groups span a large range of topics, from active galactic nuclei to strong lensing. So we are a broad church, so we do a lot of different things. Makes it difficult to organize sometimes, but I think the heterogeneous nature of what we do also makes it interesting in many ways. And of course, just like other science collaborations, we provide input to the project. So I'd just like to point out, for those of you who are providing in-kind contributions, you will end up interacting with Brant Robertson and Pierre-Alain Duc, who are our in-kind operations managers. So they will help you design your contributions going forward. And then we have various people who help us liaise with various parts of the project. Okay, so the kinds of things that we are going to spend most of our time doing over the next couple of years at least. So managing these in-kind contributions will be a key thing for our science collaboration. So I've listed a few of the topics that these in-kind contributions are going to address. So low surface minus science is a major theme in our science collaboration at the moment. So we're talking about things like sky subtraction, which preserves this low surface minus flux in the images, detection of low surface minus structures. We are interested in developing, of course, photo Z and SED fitting pipelines, because this is where the physical parameters that you need to do your extragalactic science are going to come from. Morphological parameter estimation is another big topic. There are distance measurements to SPF and things like that. And so some of these actually will be covered in some of the talks that that we'll have in this session. And then the other thing that we're interested in, of course, is cross-matching LSST data with ancillary data sets, because there are big gains to be had when you combine optical data with data in other wavelengths. Okay, and then we usually have regular telecons, so we meet once a month. So the telecons switch between sort of US-friendly times and Euro-friendly times, so everyone can sort of contribute. We also have face-to-face meetings like the one here, and some of our working groups, for example, the low surface brightness working group, they have their own activities in a form of challenges and things like that. So that's an overview of what we do. So let me just finish off by mentioning another session. So there are two sessions which are relevant to LSST Galaxies folks at this meeting. So there's this session, of course, right? And we're going to talk about sort of Galaxies related science in general. There's also a low surface, there's a session dedicated to low surface brightness science tomorrow. So this is at 4:30. It's across the road in the auditorium. And the reason this session is going to be hopefully useful is because the low surface brightness regime is basically the discovery space of LSST, right? So the things that you cannot access with previous surveys are things where the flux is essentially too faint for you to see them using, let's say, surveys like SDSS. So in this session, we're going to sort of give you a description of what the discovery space looks like, and we're going to update you on the pipeline infrastructure work that's being done to enable LSB science using LSST. And then there are going to be a bunch of talks which are going to go through sort of typical sort of extragalactic use cases in this regime, so you can get a feel for the kind of discovery science that you'll be able to do using LSST images, assuming we are able to preserve this LSB flux, which we hope to do. Okay, so I'll stop there, and I guess I'll take some questions before we start with the science talks. Thank you.
No? Yes, you can hear me. Do we have any questions for Sugata? Doesn't seem so.
Well, I have a curiosity about that. Thanks for the call. So you said that we have Geralen and I remember the other name for the in-kind contribution, liaison. I don't know. I'm thinking we as the Italian community, we already have our in-kind contribution well defined. I think that probably will be covered in the next talks, but during next days and sessions. But what is expected to be the exchange that we have with our internal in-kind contribution liaisons?
Okay, yeah. Okay, so yeah, I think that's a question that many other people will also have. So I think, yes, you're right. So from the in-kind contribution from the Italian community has work packages which are fairly well defined. So so the kind of interactions you will have with the science collaboration is mainly in the form of fine-tuning what you will produce, right? So for example, if you are offering some sort of catalog, then what are the parameters that go into the catalog, what will be useful for the science collaboration. So your conversations may be perhaps more superficial than other contributions where what is being offered is not necessarily very well defined. And there are contributions like this. So what Brandt and Pierre-Alain will do is they will essentially work with you just to make sure that you're happy and we're happy, right? And you produce something that's useful for the science collaboration. But we don't want it to be rigid, right? So it has to work for you and it has to work for us. So yeah, just have a conversation with them. And if you need more information from the SC, if working group leads need to get involved, then we can do that as well. So it's meant to help you essentially, rather than to hinder what you want to do.
Are there any other questions?
So our next speaker is gonna talk us about the galaxy morphology with machine learning and LSST. Our next speaker is Ilin Lazar.
Right. Okay. Hi everyone. I'm Ilin Lazar. I'm a PhD student at the University of Hertfordshire, and today I will talk about a unsupervised machine learning method built to distinguish between different morphological types of galaxies, especially aimed at upcoming big data surveys such as LSST, GWST, or Euclid. So just to give a brief overview on what has been done on the morphological classification in the past. Traditionally, morphology was measured via parametric or non-parametric methods such as constitutional symmetry, smoothness parameters, different types of pseudosig fitting, mid-system, Gini, M20 coefficients, and many other methods. But over the past couple of decades, with the arrival of big data surveys, there has been a strong movement towards more automated measures. And that's been done especially with the aid of machine learning. That comes in two flavors, supervised and unsupervised. Just to give a brief example on what I mean, a popular example of supervised machine learning is the work done on Wansel et al. 2020. Yeah, that uses convolutional neural networks to distinguish between different types of barred galaxies, which I thought they had really accurate models for that. And of course, to go into unsupervised examples, we have the work done on Spindler et al. 2020 and Cheng et al. 2020 that use convolutional autoencoders for both finding of strong lenses and galaxy morphology classification. And also the work that I'm going to present today, which has been engineered in Martin 2020. We know that the major disadvantage of supervised machine learning is that they are actually calibrated against visual inspection. So we need training. We need labels for our training sets to do that, for them to work. Although this is highly accurate, they can produce a variety of galaxy morphologies. This can be time consuming because of the human factor. And taking into account that big data surveys such as LSST or GWST will produce petabyte to exabyte scales of data in the coming decade, which will need studying, we will need machine learning for fast data processing and accuracy, also along with visual inspection. That's if we want to do this with supervised machine learning. On the other hand, unsupervised machine learning does not really require training on labeled data. It is built to minimize the human intervention, and it provides an advantage in actually finding rare and peculiar objects or even unknown objects in the universe. And just to give a brief overview on the structure of the algorithm, which I'm currently developing, the main idea actually comes from Hawking et al. 2018, and which has been also improved in Martin et al. 2020. So the algorithm basically starts with extracting patches of about twice the PSF size of the survey from multi-band survey images of galaxies, and calculate their radial Fourier transform profile, which then are produced, which then this produces patch vectors, which are then appended to a data matrix, which will constitute the initial feature space for the algorithm. This space is then reduced in size using granular gas network algorithm to produce basically a topological map of sample vectors, where each vector basically represents a group of similar patches. This space is then further reduced in size using hierarchical clustering. And the resulting model, we basically use it on the original data set to assign a type labeled to each patch vector, which corresponds to different visual properties. Then the next step is basically to generate a histogram for each object containing all its patches, where each bin basically represents a different patch type. This concludes with the final step, where we actually use k-means clustering on these histograms, which correspond to a galaxy. And we end up with having about 150, between a number of 150 and 200 morphological clusters, each having a certain visual property. And we actually label these morphological clusters based on the visual inspection of a representative sample from each morphological cluster. And just to show you an example of some results that we have using the algorithm on HSC data. So we can see that we actually have, the algorithm is able to distinguish between the most general morphologies, such as spirals, ellipticals, but can even go into more detail, actually looking at elliptical mergers, high ratio mergers, or even clumpy disks. And also, this can also be used for outlier detection. So if there are objects which actually don't want to you don't want to have in your sample, this can actually filter out any stars that you actually have in your dataset. So when we go from ground-based observation to space-based observations using HST candles data, the picture changes just because also the resolution is better. So as you can see, the morphological classification is actually more detailed here in terms of the concentration of the galaxies, color, and different types of morphologies. And just to give some numbers on the processing time for this algorithm. So it takes about less than 30 hours to process all the HSCDR3 deep fields. That's about 30 square degrees. And I just want to take this moment to reinforce the point that I made at the beginning, that we will actually be expecting significant amounts of data, not only from LSST in the next decade, but also from other surveys like GWST and Euclid, which will provide twice the resolution and over 15,000 square degrees of sky coverage with over 10 times the sensitivity of current facilities. And just want to mention that this algorithm is also a good way of condensing significant amounts of data to just a couple of, a number of between 100 and 200 morphological clusters, which can then be easily labeled. And just to make brief point here on how the results for the from the algorithm match the literature. We have actually put the most general morphologies that we get, morphological types that we get from the algorithm on a color mass diagram. And we can see that we basically retrieve what we see in the literature with the right locations of the blue cloud, red sequence, and the A0 green valley. Then when we look at the SFR mass relation, we do see again the star forming main sequence, and then again for fixed mass, we do see that the majority of spirals retain high levels of star formation as opposed to ellipticals, which are more in the quiescent side. And of course, when we look at the star mass distribution as a function of redshift from high redshift to low redshift, we do see again ellipticals the high mass and spirals the low mass, and basically an increase for the intermediate masses of ellipticals as we get close to the present day. So we do retrieve some of the main trends that we see in the literature, which is quite nice. And just to wrap up, for future plans, we actually try to release morphology catalog for HSCDR3 for the deep and wide fields, which we hope it will be done by the end of the year. And we try and implement the algorithm on the Rubin Science platform and actually make this algorithm available to the LSST community and produce catalogs for LSST, the data releases. Then we also plan to use this method on upcoming big data surveys such as Euclid, GWST, or SKA. And while I'm on that point, we are planning to actually improve the accuracy of the algorithm by experimenting a bit with adding more bands to the feature space, like infrared or UV. And of course, if you would like to talk to me about this, you have any questions or anything, this is my email, and also on Slack. This is what I had to say. Thank you very much for listening.
Can you hear me? Well, do we have questions?
Aside from the relatively long runtime, it looks like 20,000 hours for LSST sample. Aside from that, would you say that the existing methods that people applied to existing data sets like HSC, are they sufficient, or do we need to think of new methodologies, improvements in these methods, or do you think they will just work out of can?
So I do believe that with the high cadence of LSST releases, we will need something that will have a faster output. I would encourage people to look more into unsupervised machine learning ways of doing this. There are also really good supervised machine learning algorithms that can actually use training sets, for example, from STSS on other surveys, and then do the labeling and then do the classification on other surveys. But we actually, just because the LSST will have this high cadence, and will obviously have different depths, different. This can be, I think, this can be difficult undertaking. So, so I really do encourage people to experiment more with unsupervised machine learning, because I've seen in the literature in the last years, actually, I've been really, it was really nice to see that people have actually started using unsupervised machine learning. There's not so many papers out there with convolutional neural networks and supervised. So it's always a good idea. Yeah.
Okay. Do we have any more questions, Robert?
How are you making use of the multi-band data? Your samples looked as if they were sorted by redshift. There were certainly some high redshift ellipticals and some low redshift ellipticals. So are you mixing photo Z information with morphological information in your classifier?
No, so we actually make cuts in redshift, and then we produce models of different cuts in redshift. So we do not mix the redshifts in that case. And then we basically gather, we have like at the end, we actually combine all the galaxy histograms that we actually get at the end with the patches, and we actually cluster them. So it's we can also talk about this at the end, but I can give more details there if you like. But yeah. The results that I produced there, that's an old version of the algorithm. I also have a newer version, which is actually done the split between redshifts. So I think that version, in that version, they were mixing the redshift. So yeah, we can talk about this.
Okay, thank you very much. So we move on to our next speaker. It's Gabriele Riccio, and he will tell us how to get ready with for LSST.
Okay, so thank you. Hello, everybody. Thank you for this opportunity. So today I will talk about a little bit how possible way to use LSST data to estimate important galaxy physical properties for main sequence galaxies, and using their spectral energy distribution. So first of all, we know that galaxy can have very different properties and characteristics. So for example, we can have different morphology, elliptical, spiral, irregular. We can have different mass and dust content. We can have different star formation rate. But these characteristics are giving us important information about what is happening inside the galaxy. So for example, the processes that at the end create the emission that we observe. And so to estimate these parameters is very important. And we know that there are different ways to do it. So for example, if we take into account the star formation rate, we can use emission lines. For example, age alpha that is probing the star forming region of galaxies. But also if we look at the UV and the IR continuum, we can use it to estimate it, because we know that newborn stars emit in the UV, and then the dust that is surrounding this star forming region is emitting this light in the infrared emission. So we can use all of those ways. But if we are lucky enough to have multi-wavelength coverage of our sample, so for example, we can have UV to far infrared, but also X-ray, radio, and etc. It is better, is actually shown that it's better to use the spectral energy distribution, to study the spectral energy distribution of these galaxies to estimate the parameters. But what it is, the SED? It is basically the broadband emission from X-ray to radio. And as I said, if we are able to model each part, each component of the SED, we can use this modeling to estimate the parameters. So for example, as I said, UV and far infrared can give us estimation of the star formation rate, but also, for example, the mid-infrared part of the spectrum can give us, that is basically emission from dust, some AGN component, PI age, can give us information about the metallicity. And the sub-millimeter part, that is the thermal emission from cold dust, it is like a good probing of a good proxy of the dust mass that can be important for several reasons. But so we understand that we need to fully understand galaxies a much wider coverage of the spectrum. So why in this work we focus on LSST? You all know here for sure all the information about LSST, but what I wanted to stress is that at the end of the 10-year survey, we are expected to observe a lot of galaxies. So here is it is written around 20 billions of galaxies at the end. And of course, those observations, those data will be very high, very deep observations. So what we expect is to have a big sample of unknown objects that probably will not have any counterpart in other surveys, such as infrared survey, UV survey, and etc. So, but as we know that LSST will just probe this part, so visible plus near infrared, how can we use it to estimate these parameters that we are interested in? So to answer this question, we select a sample of 65,000 galaxies from the redshift range 0, 2.1 to 2.5 from the HELP survey. And we use HELP because as we need to compare these properties estimated with LSST with the real properties, we have to estimate it, and we need a full coverage between UV to far infrared. So Herschel is actually giving us very good mid-infrared, near infrared, and far infrared observation. So we are using it for this reason, but also as a starting point for estimate to simulate the LSST observation that we will use in the work. So to estimate the parameter instead, we are fitting the spectral energy distribution. To do that, we use the code investigating galaxy emission SIGAL. So what it does is basically building a grid of simulated SEDs that at the end will be fitted to the observed data. And to do that, different modules are used that are simulating each component of the SED. So for example, the emission from the stellar component is given by the double contribution of the some star formation history function plus a simple stellar population model to build the composite stellar population. Then, for example, emission line are simulated by nebular module. We have dust attenuation laws plus dust emission model to simulate the mid-infrared, far infrared emission, the dust emission in general. Then we can use some AGN model, X-ray model that more recently was developed, and also radio model to finish the full SED of the galaxy. So at the end, these are the models that we are using in this work. So if after you are more interested in this in detail, you can ask me better. But at the end, a grid of SED is formed, is created, and the best SED, here I'm showing one best SED for one object, and so they are fitted to the data. But also we have to simulate the LSST observation. To do that, we just take for the magnitude the values that are on the best SED that we can fit, while the uncertainty are by the definition from Ivezic et al. 2019, that for sure you know this formula. So here are just an example of my sample of magnitude error for the LSST object in function of the magnitude. So results. The first thing that I want to show you is the main sequence. So the star formation rate in function of the stellar mass for our sample. I don't know if it's possible to see here. Maybe I choose the wrong color. But still, I have here a comparison between the parameter calculated with LSST in orange in comparison with the real one, let's say, from the UV to far infrared sample. And we can see that for low redshift object, with LSST we cannot sample, we cannot calculate low star formation rate object. In fact, we have a clear difference that this disappear in going to higher redshift. If we want to quantify this difference, here I'm showing the ratio of the parameters defined as here. So the parameter calculated with LSST over the real one. And we can see that for the star formation rate at low redshift, we have a big difference. But for the stellar mass, for example, we have very similar results in both cases, in both runs. So we basically are very well estimated the stellar mass with LSST, but that's because the stellar mass is coming directly from the optical observation because it's probing all the stellar population that is emitting in that band. So we cannot use in this way, and not only the star formation rate, but also other dust-related parameters such as dust mass, dust luminosity, have this different. this difference. So how can we correct this? The first thing to think about is just basically understand which bands we need to add with LSST to have good estimation. So for example, here I'm just adding mid-infrared observation. We can see that the overestimation here, the difference is completely corrected. But also if you add UV estimation, we have much way better results. But as I said before, we can not be so lucky to have counterpart in other surveys. So how can we really use just LSST to have these dust-related parameters? And so for the dust result, I have an answer on that. Let's say that we could use the stellar mass that is very well estimated, because as the stellar mass is a proxy basically of the previous star formation phenomena, that is where the dust in the galaxy is formed. As we know, the dust is basically coming from the evolution of stars. We can link the stellar mass with the attenuation in far UV that is basically done by this dust. So there exists, and there were studied already in literature, some formula that links these two things. And so if we know very well the stellar mass, we can have the attenuation in far UV, and the attenuation in far UV is directly connected with the stellar mass, dust luminosity, and etc. And so if we use, for example, in Seagull as a prior, together with LSST, the attenuation in far UV, we can correct the overestimation, even though the errors are pretty big in this sense. So as conclusions, I think I am in time. We can use LSST to calculate these parameters, but what we need is always some kind of prior knowledge of our sample. So for example, can it be either some ancillary data, mid-infrared, UV observation, etc., or we must have some knowledge about relation that can help us to use the stellar mass as a proxy, as a starting point to estimate then these dust-related parameters. So thank you so much.
Do we have any questions for Gabriele?
It's not really a question, but a comment which I want to make, since we have lots of Galaxy experts in the room, and Galaxy people usually care about the depth of data. One of your slides claimed that the co-edit data would go to 27.8 in R. That's a slight misinterpretation of documentation, because if you read carefully science requirements document, it's defined for fiducial observing conditions, which we will not achieve in reality because we cannot always observe towards zenith, etc. So there is a great new paper by Bianco et al., where you can get the best current estimates of how deep would data really be, given all the effects of air mass, etc., etc.
Yeah, I was referring to the 10 years co-added magnitude limits that are cited in literature presently, but yeah, I was not aware about this, so thank you for the comment.
Any other questions? Oh. We have an online question from Nuskia. I was wondering, how accurate can the mass estimates be for the smallest dwarf galaxies in your data?
That's a good question that I actually don't know. Well, in general, when you have optical, very good optical and near infrared observation, the stellar mass are in general very well estimated with SED fitting. So I'm not sure exactly for dwarf galaxies, but maybe I can check, and you can write me an email and we can discuss. Yeah, thank you.
Okay, let's thank Gabriele again. Okay, our next speaker is Michele Cantiello, and he will be talking to us about surface brightness fluctuations.
So good afternoon, everybody, again. It's a pleasure to be here. I have the opportunity to present a work that has been done in collaboration with a bunch of colleagues in the last few years for an in-kind contribution of the LSST. And the work I will be presenting, though, has been the hard work has been done by Nandini Azra. She's here, and she has a poster on this topic. So check that out. The SPF, surface blindness fluctuations, are a distance indicator. Even in the era of James Webb Space Telescope of LSST, we still need these distances. It's not only for the well-known H0 tension, but in most cases, when you do astronomical studies, you need to set the stage by knowing the distance of the target. Here, I reported 3 cases in which the distance of the target was extremely important. And actually, in one case, there was a very heated debate, and still a kind of heated debate. And these 3 cases are not, I mean, are correlated to SBF, because for all these 3 objects, M87, 1052, DF2, and NGC 4493, the most accurate distance, or the most accurate distance up to a certain point, I'm referring to this galaxy, was derived using SPF technique. So what is this method? For those of you, I mean, I'm sure you all know about that, but just a quick overview. This was introduced in the late 80s by Tonria Schneider, although the idea on the basis of the method is kind of relatively much older than that. The technique allows you to get extremely accurate distances on single target based not on serendipitous discoveries. You target a galaxy, and if the observational conditions are okay, you can get the distance with an accuracy of 5% for bright massive objects, whereas for lowest LSB. Basically, you can apply this technique on all relatively smooth galaxies, and from the ground, probably with LSST, we can get to 100 megaparsec, maybe more, obviously, and for sure, more than that from the space. The basic idea is very simple. Here you have 2 images of 2 galaxies which look like similar. One is M32 behind the corner, less than 1 megaparsec. You see that the surface blindness is very bumpy. The other one is a galaxy that appears much smoother. It's 100 times more farther away. And clearly, so this quantity, this granulosity, the bumpiness correlates with the distance. So in the approach defined by Tonria Schneider, again, this granulosity is quantified through a quantity that directly correlates with the ratio, actually is the ratio of the second to the first moment of the stellar luminosity function in the observed target. How do we measure the SBF magnitude, which is normally indicated with the little m bar? It's a kind of, I would say, lengthy process. It entails several steps. I'm not going to go through the details, but you need to model the galaxy, subtract it, and mask the residual sources for fluctuations. One of the most let's say, biasing terms for this measurement is estimating the non-stellar fluctuation, the spurious fluctuation term. Now, in well-designed observation, the spurious fluctuation term here, P sub bar, is negligible, and so you can get pretty much accurate little m bar estimates. Once you do that, the distance modulus follows as usual. Little m bar minus big m bar, you get the distance modulus. Now, the big m bar, it comes from either empirical calibrations, most of the cases they are empirical calibration, or from stellar population models, which, as I said, since the technique basically depends on the ratio of stellar population properties, fluxes, then once you have a stellar population model, you can get easily a calibration of that. So, or at least relatively easily. Now, what we expect will happen with LSST. So this is not the latest baseline of depth, actually. I took that from the LSST website, but basically the concept and the numbers which I used lead to this table here, where I reported the expected maximum distance that we can get at each given passband. Now, the most interesting passbands for distances are the I and Z band, and as you can see, we will probably it will probably be possible to get to 100 megaparsec. Actually, also in the R band, and what is it kind of cool for, I mean, I started as a stellar population modelers, is that we will probably also get SPF colors, which are not of great interest for distances, but they are very interesting for stellar population studies. As everything with the LSST, this is going to be a great chance, this kind of analysis. But it's also going to be a big challenge, because we expect that at least 10 to the 4 or more galaxies will be measured with this technique. And that's why we proposed a few years ago, we started a few years ago with a bunch of colleagues again, to think about what we need to do to use this technique for this future, facilities like LSST, where you reach a huge number of targets, while the SPF technique is presently has several measurement pipelines which are thought to be single target oriented, because taking the measurement, the SPF measurement for a galaxy takes from a couple of hours, in the best cases 2 days, which means that it's not feasible for thousands or hundreds of thousands of targets. So that's why we proposed this in-kind contribution, to try to get to develop the most automated possible pipeline, a pipeline that requires the least intervention from the astronomer. Also because, well, we have, as I said, we expect to measure SPF in multiple passbands, and beyond that, something that also already mentioned Sugata in this talk, I'm personally biased by bright galaxies, but LSST is going to be a great discovery machine for LSB galaxies. And this technique is one of the few distance indicator which is accessible to these faint galaxies. So again, we started testing, we proposed this in kind, and we already started testing our procedures using, for the moment, using HSC SSP data. Okay, and for the moment we have a very well-defined schedule of what we need to do and at the status of our procedures, that we already identified a number of targets from the HSC data set. We used data release 2, and we identified a number of targets which already have SPF measurements from the Tonry and collaborators SPF ground-based survey. For the moment, we already have several modules like galaxy modeling, subtraction, PSF modeling, and optimization, the power spectrum analysis. But we hope that in the next few months, these steps will also be completed, like power spectrum fitting. As I said, one important thing is the estimate of bias, P sub bar, and then the calibration, which should be kind of straightforward. What is interesting is also how much, something that we need to figure out is how much this SPF magnet is unharmed by the data reduction pipelines. Again, this work has been done by Nandini Azra. She has a poster. We probably can check that out online. And let me leave you with my summary, which I'm not going to read because that's it. Thank you.
Thank you very much, Michele. We have a question here.
Sorry to ask all the questions. We had a student in Princeton who looked at the HSC data for SBFs, who was Scott Carlston. I wondered if you had looked at his results and figured out how well that would work. So that's the first question. The second is, HSC seeing is probably significantly better than Rubin seeing, certainly in the early days. We get down to 0.45 arc-second. So do you have a feeling for how much the presumably slightly less good image quality will impede your work, and to what extent you can make use of the relatively low signal to noise fraction, you know, the top quartile of the seeing, and how that trades off? So
okay, for the we know perfectly well Scott Carlston's work. He's been actually is more, as I said, I'm mostly biased toward the bright galaxy and rather than the LSB. And the LSB galaxies, they have the a big defect that they are faint, and but they have a great advantage. They don't have, or at least they have small population of globular classes, so the bias is relatively small. So it's a kind of slightly different, it's a relatively different approach. So, but the idea is to have a pipeline that works for both. Sorry, I'm not sure I completely understood your question for the mask, but to keep the mask. I think that your point was about what happens if the FWHM that we have for expected for a HSC is, I remember reading something like 0.7 is in the I band, is something like that. Am I wrong? Yeah. Okay. So, but clearly, I can tell you the direct experience I had with the NGVS survey, the Next Generation Virgo Cluster Survey, for which I led the SBF measurements. In that case, the I band seeing range, it's a 4-meter telescope. The I band seeing ranges for something between 0.65 at best condition to 0.8 something in the I band again. And we were not expecting to get much farther than the Virgo cluster, which is in there, but we actually succeeded in measuring distances down to 40 megas a parsec. And the survey depth is there in the I band is 25.8. So it's 1 magnitude fainter than expected for LSST. So if you have, we didn't make any simulation yet, so the numbers are just based on my feeling. My feeling is that if the FWHM would be around 0.7, which I guess it's an average value, reaching 80 megaparsec would be kind of feasible. Ed is there, maybe he can add more because he has more experience than me on this topic. He's one of the precursors of this technique. But in the best, the places where the seeing is good and that we are not limited by the crowding of globular clusters in the very center of the galaxies, I am optimistic to get to 100 megaparsec. But we need simulations also for that, and we're thinking to use DC2, at least to improve DC2 data. We need to add the SBF signal, which is not there.
Okay, let's thank Michele again. So our next speaker now is Kasia Malek. and she's going to talk us about the dust in LSST.
Yeah. Thanks, Abel. Thank you very much for having me here. I know that the dust in the LSST sample is a bit controversial to study, but I think we all need to do it. So first, maybe I will start that this work is done with my group. So Junai, which is sitting there, if you can raise your hand. And Misha Hamed and Gabriele, you know already, now he is in the LOC. So we are working together on this LSST data, but you know, I wanted to give a long introduction, but I think Gabriele did it very well. So just want to mention and stress that all the galaxies, it's for all the galaxies, the mixture of dust and stars, it's super important, and we have to solve somehow this mystery, even with the LSST data only. And we know that we have a different kind of galaxies. What we can really do with LSST, we can study their morphology, and we should somehow gain from this morphology more information, at least in my opinion, for our study. And no matter what, if we have the morphology or we have other parameters, we would like to somehow classify galaxies, yes? We want to do the bins in the redshift, yes? So it's something that we have to calculate, the photometric redshift. We want to do the bins in the stellar masses or the star formation rate to study galaxies and their evolution, not only the single galaxy. But how to do it? As I said, I think that's my personal opinion. With morphology, we are super safe. Yes, we have a lot of techniques which we saw on the very beginning today during the talks that we can obtain very good morphology for our galaxies. I believe that the same is for the redshift. But what about the stellar masses and the star formation rate? So the main physical parameters. And we know that dust is a very important component of the galaxies, but it can also mix a bit our vision, yeah, and our knowledge about the galaxy. So dust is the main component of the interstellar medium, but we have some outflows, inflows, and you know, it's a very dynamic mixture. But how we can really see the dust in our galaxy? So first of all, the easiest thing is to look at the infrared emission. Yes, but what if we don't have the infrared emission? Then we have this modification, which was also shown by Gabriele, the modification in the stellar continuum between UV and the near infrared band, when the dust attenuation plays a significant role. So as you also saw it before, like we have in the perfect case, when you have a full SED and we can see the galaxy in the very holistic way, we can somehow calculate in the direct way the star formation rate. Then in the mid-infrared part, we have information about the dust properties, metallicity, and etc. And then in the infrared part, we have the hidden star formation rate, which is related to the attenuation. So we have those newborn stars in the clouds of dust, which first absorb the emission from 0.1, 0.4 micrometers, and then re-emits it in the infrared. And it's rather huge change in the galaxy. You can see here, this is the amount of the dust of the energy attenuated by dust and re-emitted then in the infrared. So we have to take it into account. Still, let's stay in the perfect world. This is the example of the galaxy from Dustpedia. Here you can see the very nice detection of those galaxies from the far UV to far infrared. So we can think that we can study this galaxy very, very well. Yes, so we have all the information. So we can link our observation with the young stellar population, with the dust properties, and etc. and etc. But to mix, like to make a global fit, like the global, like holistic view on the galaxy, we have to somehow link the stars and the dust in the same time. And for that, we are using the dust attenuation laws. We have three very popular attenuation laws in the literature. It's a Calzetti, which is single power law, or shadow and fall, when we have two power laws, one for the bird cloud and one for the interstellar medium, which is somehow more physical, and then some other modifications. So we can take our observation, we can use the energy balance, which is exactly what the attenuation law does. And we can calculate all the properties for the galaxy here, the properties from the Dustpedia. But it's not exactly like that. So with the attenuation, even though the attenuation are not very different, they can result in completely different results for the estimated parameters. Here, for example, you have an example of 42 galaxies from the HELP project. So the galaxies observed also in the far infrared. And I calculate the stellar masses for all of them using 3 different attenuation curves. And you can see that even the solid parameter, which is the stellar mass, can differ using different attenuation curves. And all the fit looks really good. It's not that some fits were much worse than the others. And here's the example of Misha Hamed work. When we have this is the single galaxy observed with ALMA, and then calculated the stellar mass and the star formation rate. Here's the specific star formation rate using different attenuation curve. And the results of this galaxy, there are those 3 points. So you can go from the really main sequence, typical main sequence galaxy, to the galaxy which is more like star forming and star bursting. So this is something we should remember about using attenuation curve. And this is the result from Gabriele, which we saw just a moment ago. So if we use only LSST data, we have to somehow correct the star formation rate we obtain at the end. And here Gabriele used as a prior the attenuation in far UV. But how to obtain the attenuation, like this prior for our SED fitting before SED fitting? Of course, what also Gabriele mentioned, we can somehow create to construct a global attenuation in far UV stellar mass relation for different type of galaxies at different redshift, and it can be a bit complicated because also we have galaxies we do not observe before, so we have no idea what the relation looks like, and it's also a bit complicated. But my approach, and I don't know the final result yet, is can we use the information from LSST only to obtain this information? Because we have a beautiful morphology, we have very good magnitudes and fluxes at the end. Why not to use this information? So I hope that now my motivation is clear. I really want to use only LSST data. The idea about this work is coming from the Véronique Buat paper 2019, when we analyzed a very small sample of dusty galaxies, like 17 galaxies. And she found that using the ratio of the H-band radius to the ALMA radius, she can somehow predict how steep the attenuation curve should be. But this is a dusty galaxy, yes, at redshift 2. Then in the next work, Misha is going to present it soon during the poster session. Misha found that for 300 galaxies, still ALMA detected galaxies, we can first of all, from the ratio between optical or radio and the ALMA radius, we can first of all predict which attenuation curve to use, so steeper or more shallower, but also he found a very nice evolution with redshift, but this is his work and he's going to talk about it. But okay, we were still in the dusty part, and then Junais is coming with his result, and Junais found that for the low surface brightness galaxies, here we have the dust luminosity over stellar mass, and here we have a surface brightness, that we, even for low surface brightness galaxies, we have dust, and we have to take care of it. We cannot neglect the dust in those galaxies. So this is something we should think about, and you can discuss with Junais later on about all the details. Okay, and we know that attenuation is most effective in this very narrow range of wavelengths between 0.1 to 0.5 micrometers. So this is exactly the range we can observe with LSST. So we did a very short work. We used the 2 catalogs. One is the Galaxies DSS WISE legacy catalog prepared by Salim 2016, and he calculated all the main physical parameters from the SED, from the full SED. So we have a stellar mass, star formation rate, and attenuation in different filters. And then we cross-correlated this catalog with ALAM 2015. So it's the SDSS data release 12, in which we have radiuses and magnitudes for those galaxies, yes, with the U, G, R, and A bands. So similar to LSST. And so then we we calculated the surface brightness radiuses for those 4 bands. We cleaned the sample. So we now at the end, we have 88,000 galaxies for redshift lower than 0.2, when we have all the physical properties plus radiuses and attenuation. And what we have found, that we can use only surface brightness ratio between, here is between U and R band, you have more, and the attenuation, and we can see the relation. Okay, here it's not very visible, it's better visible with colors. But if we go, for example, here, when we have on the y-axis, we have the ratio between surface brightness in G and R and I, and here with the U in U band, you can see clear coloration between the attenuation. So here is the color code with the attenuation in far UV, and we can guess even from this SDSS data and the very rough estimation of the attenuation, we can guess the prior. Here just the examples of different galaxies on this plot, so you can really see that using radiuses and information about the morphology, we can really check in which galaxies we have more dust, which can attenuate and then influence our final results. We can also stay with G filter only, but then the parameter space, it's much more narrower and we can make more mistakes. So that's why I'm super happy that we have the U band in LSST. And it looks that using only photometry, we can really at least estimate the attenuation in far UV, which can be used in the next step for the calculation of the stellar mass transformation rate and etc. Just to say a few words about the results again. So we need attenuation in far UV to calculate proper star formation rate for LSST only galaxies, which was shown by Gabriele. We know that the slope of a dust attenuation changes with ratio between UV, radio, and the ALMA bands. It's something that Misha Hamed will tell you. We have the dust in the low surface brightness galaxies, which are super important for LSST. And we found that we can at least guess the attenuation in far UV using only LSST, and I hope that we can use it to calculate all the physical parameters from LSST to study them more detailed. And that's it. Thank you very much.
Do we have questions for Kasia?
Thank you for this beautiful summary. I have a question about what you could tell us about depths that we need in each band. The current plan is based on optimization of photometric redshift without paying attention to how well we can determine physical parameters. Yeah. Can you and your group perhaps tell us if we should think about going, say, half a magnitude deeper in new bands, since it's so important, at the expense, for example, of killing 0.1 magnitude in all other bands? Can you give us any input to the trade-off based on the physics that you're studying?
Mm-hmm. I wanted to say that it's a very good question, but I cannot, so I will not tell it. Say it, but yes, I think that we need some more time because now we use only SDSS data and Salim, but we want to go into the simulation from LSST, and then we can check how deep we can go. And but this is the next thing we are going to do. We discussed with Dunais that this is the main work we are going to do just after the conference. So I hope that soon I can give you the answer. Thank you.
Okay, let's move on to the next speaker. Thank you very much. So our next speaker is Crescenzo Tortora, and he's gonna talk us about convolutional neural networks.
So hello everybody, thanks to allow me to talk about GalNet, which is our convolutional neural network to study surface brightness profiles and derived structure parameters. And this is also a subject of an in-kind contribution within the enough community. This is a work which is done by Rui, Nicola Napolitano, myself, and other people. So all of us, we are here in this room as we have similar objectives. Among these, there is the possibility to study the structure and the morphology of the galaxies. For example, we know that measuring the size evolution of galaxies as a function of redshift and comparing this evolution with the expectation from simulation means that we, in some sense, can constrain the mass assembly of the galaxies. Or, for example, this is something I'm interested in, we can search for particular classes of objects, like, for example, Rayleigh galaxies, which are these special galaxies, which are the remnant of very high redshift red nuggets, which for some reasons missed the merging phase, and they remains constant till now. So we have done some work in the last years about searching and characterize this peculiar class of objects. And finding this object means to measure the size of these galaxies. And you see in this plot here how we select typically this object by departing from the average size mass relation in the galaxies. For doing this kind of job, we need to measure the structural parameters. So you see here an example of some on the right side, an example of a surface brightness profile fitted with Cersei profile using the code 2D4, which is a code which is using a standard approach by fitting a Cersei profile and minimizing a chi-square. This means that we need, for this kind of stuff, for this kind of purposes, to measure very precise structural parameters. And these parameters need to be measured for a large number of galaxies. Since, for example, in this case, we need a large number of galaxies in which we can find these very extreme rare objects. And on the market, there are a lot of codes, okay? One of these is the 2D4 code I was mentioning, made by Francesco Barbera. We use this code within the KIDS survey, KIDS DR3, to measure the structural parameters in GR and I for 1 million of galaxies. Of course, this needs a lot of time to process all this data. And recently, other codes, the code in orange, are a few of the codes that are on the market, have been analyzed in these two Euclid paper as deep legato, who is approaching the problem from the machine learning side. And to this list, and there are also other on the market codes to fit Cersei profile to the data, there is also GalNet, which is this our code. You see the paper here with the list of the author. What we can learn from this comparison is that the reduction of computing time that machine learning can allow us is the main point of using these new techniques with respect to the classical approaches. For this reason, with other collaborators, we are developing an environment in which we want to measure the properties of the galaxy, starting from GalNet by fitting the structural parameters, or, for example, deriving photometric redshift by using both imaging and photometry, and in the future also trying to estimate cell population. Let's go to GalNet. So GalNet is a convolutional neural network. We have two networks, different networks, GalNet 1 and GalNet 2. GalNet 1 is just we just input the galaxy image, okay? While in GalNet 2, we input both the galaxy image and the local PSF, okay? And the first step of this kind of analysis, which is supervised on it, so we need to train the network, we need to simulate properly the galaxies. So we had some experience in the past by simulating gravitational lenses, and we have done something similar also here. So we take a Cersei profile with all these parameters. We convolve the Cersei profile with the PSF. We just search for random cutouts in the survey we are going to analyze, in this case, KIDS. And we put on in the middle of this cutout the Cersei profile simulated with PSF. At the end of the story, we have a mock image, okay? In this way, we can reproduce the characteristic of the survey. In this way, we can eventually input in the image some companion galaxies, which can make more complicated our analysis. And these are other examples. Of course, this is done by training on a large number of galaxies. and testing both on data and also on real galaxies for which we already have some structure parameter by 2 default. And we are limiting in this analysis to a high signal to noise ratio data, since we have demonstrated with the classical method that with a signal to noise ratio larger than 50, we can reproduce quite well the structural parameters. So these are some results you see in the different panel, all the parameters from magnitude, effective radius, PA, Q, and the Sersic index for both network. You can see that the agreement is quite good. Also, if in the GalNet 2, the agreement is better, as we can see now. In fact, in this table, you see some indicators. And I want to that you point some attention to the effective radius, where you see that all the indicator, the correlation among output and input, the fraction outlier, and NMAD are improving, moving from GalNet 1 to GalNet 2. And this improvement is also getting better and stronger if we consider the Sersi profile. You know how difficult it is to constrain the Sersi profile. You see also here some images for 12 galaxies, where you see the image and the residual for GalNet 1 and GalNet 2. You see in general, the residual are quite good. And the first conclusion is that GalNet 1, which consists in inputting just the galaxy image without the log RPSF, is obtaining quite good result. But there are some cases that you see here where GalNet 1 is not able to learn properly the log RPSF. So there is some, you see, some residual in these images. Instead, inputting the log RPSF is improving the results. So these are the results. GalNet 1 is working quite good, but adding the log RPSF and GalNet 2 are working far better. This is the comparison with on the real data, by comparing the result of GalNet and the 2 default, which are just obtained by fitting a Sersi profile. You see all the parameters of the Sersi profile. The agreement is quite good. The agreement is improving if we consider GalNet 2, which means that in some way the network is not able to learn properly the PSF for all the galaxies, and we need to help the network in some way, providing the specific PSF which is measured around that galaxy on that position. Yeah, these are some examples, some more galaxies where you can see the residual for the 2 network and also 2 default. Of course, also in this case, you see how GalNet 2 with information of the PSF is working better, more similarly to standard methods. Almost close to the end. I want to focus the attention on this kind of plot where we compare the result for the magnitude for GalNet and classical approaches. Of course, we expect that this is one of the parameters we can recover far better than the other. Okay, but also on this plot, we can see some outliers. Here on the top, where 2 default is predicting brighter magnitude with respect to GalNet, you see here on the top right some example where you see how bad is the fit of 2 default. Okay, and the reason there is that there are some companion galaxies which are disturbing the fit, or probably very steep peak in the center of the galaxies. Instead, there are also these other outliers here where 2 default is predicting a faint, very faint magnitude with respect to the GalNet network, which are going to provide a brighter magnitude. You see on the right the reason what's going on, that the classical approach by just minimizing X² is not reproducing correctly the galaxy. You see here the galaxy is substantially surviving from the fit. So from this slide we can take these 3 conclusions. So typically GalNet is not presenting outliers, so catastrophic outliers. It always converges with respect to classical methods, since it is learning from just inputting a training sample, so it's not going to not converge. It's learning properly what is the main body with respect to other approaching. And this is very important, since it's able to separate from the main body of the galaxy from, for example, a compact core or an external feature on the right, or if there is a residual disk, or finally, in case we want to find, for example, strong lenses, it is able, in that case, or just ring-like features, is able to remove the main body of the galaxy and leave the residual that can be very interesting for analysis. So this is just this is the last slide. Just to tell you what are the ongoing projects. One of these is to use GalNet for the World Kids survey, 1350 square degree. Yeah, I have done. Which means obtained structural parameter for 5 million of galaxies with GalNet. And of course, looking at LSST, I remember you, as I was saying at the beginning of this talk, this is a subject of an in-kind contribution. And we have started to apply GalNet to HSC data, which should resemble what we expect to have with LSST. Rui sent me this result just a couple of days ago. We just made a very fast test. You see the comparison with the ground truth for the Cersic index and the effective radius. As you see, the results look quite good, too much good. Of course, the reason is that probably he made just a very fast exercise. He just extracted a few backgrounds, not many backgrounds. So probably the network is recognizing too easily the background is using. So the next tests are going to complicate this analysis using many cutouts for the background, inputting the Cersic profile, modeling it more correctly, and going on. But we are confident that this GalNet will be very, we work quite good with the HSC and LSST. And some more improvements are, of course, going for multi-component analysis, explore potentially the potentiality to separate stars for galaxies by modeling the galaxies, a multi-band analysis, of course, and something also we are going to explore is to give errors to these numbers, which at this moment, this network is just providing numbers without uncertainties, but there are some approach we can use as Bayesian neural network. There are some students of Nicola, which is who is working on this, so potentially we can have also errors on these estimates. And this is everything. Thanks.
Thank you very much. Do we have any questions for our speaker?
The quick one. So I'm still, in the red nugget part. Are you going to search for red nuggets in LSST with this new tool?
No, we don't have any plan on this. This was but I guess this is something we can do with the. I guess this can be done with Euclid. Mm-hmm. Of course, in that case, you have something more in terms of resolution that can help a lot, since we are talking of, as you know, we are talking about some galaxies which have sizes of 0.2, 0.3 arc second. These are galaxies at redshift 0.2, 0.4. So Euclid can help more on this in terms of resolution. But I think potentially this is something that can also be done with LSST. And probably one pro of these wide field surveys is that they can observing a large scale area, also at very low redshift, where we expect that these objects are extremely rare, at the point that we just know 3 of these objects in the local universe, potentially exploring 10,000 square degree in the sky. This means that we can find some of these objects at very, very low redshift. Potentially, yes, this is something, I guess this is something can be done. We have done this with kids survey with the seeing around 0.7, so the seeing is more or less there. These are bright objects, so you can do it without any issue. Thank you.
Hi, Simona Meyer, PC and 2P3. I have a question. So you compare one method to the other, but you didn't show any simulations to see, for example, to which depth you can arrive, or where you can reconstruct the parameters. Are you planning to do that?
We have we are comparing with the simulation. You mean just simulation?
When you say you're comparing with the other method, right? To
Yeah, but before comparing with the method, the first plot, I cannot show them now. Of course, when is automatic, we are automatically comparing with the ground truth where we obtain, we compare in the test phase. Since we simulated Cersei profiles, putting them in realistic condition. We know the ground truth since we have simulated the Cersei profile. So this is the way we have to find that the GalNet is working. So the first one. So we just compare the output structure parameter with the input structure parameter. In addition to this, we also did this comparison with two default. Yeah, sorry if I was not clear.
I missed that. And so do you think that making this comparison, your new network works much better than traditional methods, apart from the speed at which you...
No, in terms of speed, of course. In terms of speed, of course, is 100 times faster. For example, just the training phase with the normal laptop would require for 2 million of galaxies in the training set less than 1 day. The training phase. The testing phase is is faster, I guess, in 1-2 hours. To model the 1 million of galaxies we have modeled with, I don't remember exactly, but it took months probably to since we did that job in GR and I for 1 million galaxies. It took a lot of time with the standard methods. I don't want to say that something is better than the other, of course, since but of course in terms of velocity, computation time, that is far better. You know, so in some cases, sorry if I just finish my comment. I think that in some cases, machine learning could also not replace totally a classical method. In some cases, it could also be considered as a guess, you know, just to provide very fast 0-point estimate for the parameters. In some specific cases, you can use more complex methods to use those parameters as input, you know, for your minimization of chi-squared, Bayesian methods and so on. But yeah, processing millions of galaxies with this approach, as you also are doing, you know, is unique.
Okay, let's thank Crescenzo again. So we are moving to our lightning talks session, mini session. So the speakers can come up. I think that we are missing one of the speakers. Liza Sazonova, not here. Okay, so our speakers are Francesco Pistis, is him, Mahmoud Hamed, here, Eunice, and Luis Suarez. I think that Luis, you have to put, you know, like in the middle. So, you know. Okay, Francesco, when you're ready.
Good afternoon, everyone. My name is Francesco Pistis. I am a PhD student at the National Center of Nuclear Research in Poland. And I'm working on the Fundamental Metallicity Relation. And in particular, I studied the effect of the biases and the methodology on the conclusion about the evolution of the relation itself. And the study of the metallicity versus the normalized specific star formation rate in different mass beams results in the least biased projection of the FMR. And it is the best method of comparison of sample at different redshift. These studies are strongly limited from the spectroscopic surveys, and with machine learning, it is possible to expand the FMR with photometric data. there are already some studies using the machine learning algorithm to estimate the metallicity from photometric bands and colors, and we plan to use this method to study the FMR itself. So if you have any question, you can find me during the World Conference or write me an email that you can find here. Thank you.
Our next presenter is Mahmoud Hamed.
So hello everyone. In this flash talk, I will present basically, I highlighted the results of the recent work that we just finished recently, which links basically dust attenuation with morphology, with galaxy morphology, with basically the compactness, the relative compactness of the star forming region across a very wide redshift range to the dust emission. And we found that at basically for very similar distribution of star forming region and the dust emission, steep attenuation curves are preferred, while shallow attenuation curves, more or less like Charlotte and Fall or double exponential, they don't have a preference across the redshifts. Thank you.
Thank you very much. Luis. Our next presenter is Luis Sualves.
Hello, hi, good afternoon. So yeah, I'm Luis Suelves. I'm doing my PhD with Agnieszka Polo and Will Pearson in SBJ in Warsaw. So my research is doing identification of galaxy mergers. And basically what we have done was to create a training data set for a neural network in which we use mergers and non-mergers obtained from the first data release of a Galaxy Zoo. This neural network, we applied it only to photometric information from these galaxies from SDSS data release 6. And the main result that we found is that using only the sky background error that we can obtain from SDSS, we obtain a very high accuracy for identification in this training set. We arrived to more than 90% of accuracy in a crash balance set, so half mergers, half non-mergers. And that was thanks to this, to what we consider is the very small signal that is mixing with the noise around the galaxies that is able to detect it in this sky background calculation. So if you have any questions, of course, I'm here for you and I can show you the poster, and also you can find me on Slack. So thank you very much.
Thank you very much. And last but not least, Eunice.
Hello, everyone. I'm Janais. I'm from National Center for Nuclear Research in Warsaw, Poland. So my poster presents the variation of dust luminosity and attenuation in galaxies as a function of surface brightness. It is generally considered as low surface brightness galaxies contain very low amount of dust, but our sample from the North Ecliptic Pole field with a set of multi-wavelength data shows that it may not be the case. LSBs could have a significant amount of dust. And from the plot shown here, with a stellar surface density, which is a proxy for surface brightness in galaxies itself, with respect to the specific LIR, the LIR as a with the ratio stellar mass, and also in the right plot, the attenuation with the same quantity. In the left plot, we can see that with galaxies, which when we go towards the fainter side, their specific LIR seems to be increasing. So it means it could be an indication of more amount of dust for a fixed stellar mass bin. And in the case of attenuation itself, we can see that with respect to surface brightness, there is a flat trend. So varying surface brightness, the attenuation is having a non-negligible value of the order of around 1 magnitude. So from this work, what we can see is that low surface brightness galaxies could have a non-negligible amount of dust, which is very interesting. And for surveys like LSST, which will observe very large number of low surface brightness galaxies, these results will be very crucial. Thank you. If you are interested, feel free to come and chat with me.
Thank you very much to the speakers. And do we have any pressing questions for our lightning talk speakers? Something that, you know, cannot wait? So if not, let's thank our speakers today to the session. Let's go for the coffee. Yeah.